Hello, hello, hello. In this worked example, we're going to work on an example related to the concept of instantaneous velocity. And to keep things simple, we are going to continue to consider just a one-dimensional world in which things are moving back and forth along a straight line. So the idea of instantaneous velocity relies on remembering what we meant by average velocity, which we did in the previous worked example. So by definition, the average velocity of an object in a one-dimensional world is just the ratio of the displacement of the object that occurs, uh, the ratio of that displacement to the time interval delta t over which the displacement occurs. And so, for example, if you had an object who had a position versus time graph that looked like this red curve here, and you wanted to talk about the average velocity during this time interval delta t that begins at time t1 and ends at time t2, well, this is how you would do it. By definition, delta x, it's going to be a positive number equal to this length here, and delta t is going to be the length of this horizontal dotted line here. That's the difference in time between the final time and the initial time. And the ratio of those two quantities, delta x over delta t, is the average velocity. And graphically, you can see that the average velocity just corresponds to the slope of this green line here that connects these 2 points. Because remember, by definition, the slope of a line is the rise divided by the run. And now to talk about the instantaneous velocity, we're just going to define uh, the instantaneous velocity as considering what happens to the average velocity in the limit, in the limit that the time interval, I'm really having trouble here, in the limit that the time interval delta t goes to 0. So we've introduced this notation here and this concept of taking a limit, which should be familiar to you from your first semester calculus course like Math 115. And we're just going to consider what happens to this ratio as we make the time interval delta t get smaller and smaller. And so we can describe this process or visualize this process graphically with the following graph that's drawn down here. And this section of the graph here is just meant to be a zoomed in picture of what's going on in this section of the graph. And in the various lines that are drawn here are considering cases in which delta t, that's this interval, the time interval here, is getting smaller and smaller. So what I want you to notice about this graph is that as delta t gets smaller and smaller, the slope of this line, that is the ratio of delta x to delta t, changes a bit. The lines are getting steeper and steeper. So that just means that as delta t gets smaller and smaller, the average velocity is getting a little bit bigger and bigger. And in the limit that delta t goes to 0, what I'd like you to see is that the slope of the line begins to approach the slope of a line that's drawn tangent to the curve at time t1. So we've argued this important fact, which is that the instantaneous velocity is given or is equal to the slope of the tangent line in our position versus time graph. So in other words, if you wanted to know the instantaneous velocity of the object at time t1, what you would do is you would construct a tangent line a line tangent to the curve. And by tangent, I just mean it touches the curve at just that one point. And the slope of this line, of that tangent line, gives you the instantaneous velocity. And again, the way you calculate the slope of any line is to take the ratio of the so-called rise to the run. So the rise is this vertical distance here, and the run is this horizontal distance here. So let's see how that works in an actual example. Actually, let me make just one last point before we move on to the example to connect with something that I'm sure you've seen in your introductory calculus course. This limit of the ratio of delta x over delta t and the limit that delta t goes to 0, that, of course, has another name. We can call this dx dt, or the derivative of x with respect to t. So the example I'd like to consider is you consider an object moving in one dimension in which its position, x, measured in meters, as a function of time measured in seconds, is given by the following red position versus time curve. And the question is, what is the instantaneous velocity of such object at time t equals 1 second? So to answer that question, I need to construct a straight line that is tangent to the curve at t equals 1 second, and then calculate the slope of said tangent line. So at t equals 1 second, we're talking about this section of the curve. So we want to construct a tangent line, in other words, a line that just glances, barely touches the curve at that point. So what's that tangent line going to look like? In order to do it, well, that's a little bit too steep. Let's try again. We want something that just barely touches the curve at t equals 1 second. So that black line there sort of looks like a good version of a tangent line. And let me try to extend it just a little bit down this way. Whoops. Something like that is my tangent line. So you'll see that this black line touches the red curve just at this one purple point here. That's the tangent line. And now we want to calculate the slope of that line. So how are we going to do that? Well, we want to, I'm just going to draw with green here. I'm going to draw sort of a right triangle here. And the vertical length of this right triangle, has magnitude delta x. Delta x is a positive number in this case. And that's the rise. And then the run this is my delta t here. And looking at the graph, we can see, I'm just going to not try to be super accurate here, but it looks like delta x has a length of about 4 meters. I'm going to put squiggly signs here to indicate that this is, I haven't tried to be perfectly accurate here. And my delta t looks like it's about 2 seconds here. So again, by definition, whoops, the instantaneous velocity at t equal 1 second is equal to the slope of this tangent line and that slope is about 4 meters divided by 2 seconds, or plus 2 meters per second. So the instantaneous velocity at a time of 1 second is plus 2 meters per second, with the plus sign indicating that the object is moving in the positive x direction. Its value of x is increasing, and we have the tangent line has a positive slope So that indicates that the instantaneous velocity is a positive number. And that's it for this worked example. Hope to see you again soon. Bye bye.